Hi, this is Professor Marty Lariviere, and this presentation is a brief overview of using the Q.XLS spreadsheet that's available on the Canvas site. This is a spreadsheet that will automate some of the calculations used in the queuing module of the course. Once you download the spreadsheet from Canvas and you go to open it up, you'll first get this dialog box. This is just warning you that there are macros in the spreadsheet and asking if you want to use them, and you do. The spreadsheet's fairly useless without them. Once you open it up, it will open to this first page, where I should acknowledge up front that this spreadsheet comes to us from a colleague up at Cornell University. This front page outlines the models that are used here, as well as presents some problems to get your hands around using the spreadsheet, just some test examples to use. Along the bottom here, you'll see that there's two pages that actually do calculations, one for a finite waiting room and one for an infinite waiting room. This is the infinite queue example that's included on the front page of the spreadsheet. It's asking about City Clinic, a clinic that has 2 nurse practitioners and an arrival rate of 45 visits per day of patients over an 8-hour day. Each of the nurse practitioners can handle 25 patients, and then we're asked a variety of questions about how long patients wait, what if some patients have high priority over other patients, and so on. If we go to use this, let's first look at the infinite queue spreadsheet. And one thing on this particular part of the spreadsheet, worksheet, we need to make sure we have sensible numbers. What numbers can we enter? Well, we can enter numbers where we have a yellow background. So this portion of the spreadsheet here, up on the right corner, is where we'll enter the basic inputs for the spreadsheet. We need to know the number of servers, the arrival rate of work, and how fast an individual server can process customers, or more accurately, the capacity of an individual server. So for example here, I've got one server. I've got an arrival rate of 45 patients per day, and that one server, that one nurse practitioner can handle 25 patients a day. In that setting, I don't have enough capacity. I have more customers showing up than the system can process, which is why I've got that red warning bar above there. If you go and look at the specific data here, you'll see I have things like negative queue lengths and negative waiting times. That obviously makes no sense. To have a sensible model, we need to have enough capacity for the system, and I can do that by having 2 servers, as I have here. Note, for the number of servers, the spreadsheet will actually let you enter a fractional number of servers. You could put in 2.38 servers if you really want. But again, that makes no sense. You should really think about only entering integers, 1, 2, 3, and so on. So that gets us how we get sort of the problem set up. We can now start looking at what kind of information we get out of the spreadsheet. The first thing we get out of this is the average number of people waiting in queue and the average waiting time. I've got those here. So we have on average 7.67 customers in the system, assuming that I process those customers first in, first out. So if I arrive before Jane, I will be served before Jane. Also, I've got the average waiting time here. Note that the waiting time here is going to be in the same time units as the arrival rate and the server capacity. So I have the arrival rate and customers per day. I have the server capacity and customers per day. I have to have consistency there. And what I will spit out here is that I have a waiting time of 0.17 days. That works out to be about 1.36 hours, assuming an 8-hour day. The next questions we're asked are about what fraction of time we have the system in different configurations. So for example, what fraction of time do we have more than 10 customers waiting? What fraction of customers wait more than half a day? Those are the questions that we were asked. I can answer those questions with these next 2 lines. And again, we've got yellow cells, so we can type in what data that we want, right? If we can ask the question of what's the probability of having more than 8 customers or 3 customers, just as well as asking about 10. We can ask about the probability of waiting no time at all, so 0 days or 0.2 days, and so on. What we find here is that we have the probability of having 10 or more customers waiting is about 26%. The probability of having customers wait more than half a day is about 7%. If you look down below that, we can also find the number of people in service, the average utilization of the servers, which we don't really need to calculate. The spreadsheet to calculate. We could have done that ourselves. We also have the total system. So how many people on average are there in the system, and the average time in the system. If you compare these total numbers for the average number in the system, the average time in the system, with the first numbers we had for the average number in the queue and the time in the queue, you'll see that they're linked by the service process. On average, we have 1.8 people in service. 1.8 plus 7.6 gives us the 9.4 we have down at the bottom for the average number in system. We can serve each nurse practitioner can serve 25 customers per day. If you look at the average wait in the queue up above, as well as the average time in the system, the difference between them is 1/25, the average service time. If we scroll further down that worksheet, we'll find information about priorities. Let me just say something here about how the assumption we're making with priorities. What we're assuming is that we're going to divide up customers into priority classes. We'll know those classes when they arrive, and we will treat the highest classes first. So if I have high and low priority, I'll treat the high, when a nurse practitioner becomes available, that nurse practitioner is going to take the high priority customer that's been waiting the longest. A nurse practitioner that becomes available will only treat a low priority customer if there are no high priority customers waiting. We're also going to assume that service is non-preemptive. What do I mean by that? Suppose a nurse practitioner is waiting on a low priority customer and a high priority customer arrives. The nurse practitioner is going to finish serving the low priority customer before they go on to serve the high priority customer. So the fact that a high priority customer arrives doesn't immediately bounce a low priority customer out of the system. In the way things are set up here, we can have up to 4 priority classes. For the moment, we just have 2. Note that we're only entering 3 numbers, the yellow boxes. We're going to have the high priority customers as the residual. If we put 0.8 in for the second priority class, the high priority class is going to be by default 0.2. So it'll just be 1 minus the numbers we put in the yellow. What we see here is that with 20% of the customers being high priority customers, there are not very many of them in line, only on average about 0.18. Their waiting queue is also significantly shorter, it's 0.02. The lower priority customers make up the bulk of the line at 0.74, and they have significantly longer waits. We can also relate what we have for the priority system here back to the numbers we have above for first in, first out. For example, if we add up the number of people in line for high priority customers and low priority customers, those sum up to 7.674, which is what we had for the first in, first out queue length above. If we take a weighted average of the waiting times, so 0.2 times 0.02 and 0.8 times 0.2, we end up with an average wait of 0.1705, which is what we had for the first in, first out wait above in the queue. So having priorities doesn't change the overall length of the queue or the average wait of customers. It just treats some people better than others. We can also start putting dollars and cents on the clinic. This is an extension of the problem here. Let's suppose that we've got some information about what the clinic receives in revenue for each customer and a delay cost or a penalty cost for each hour that a patient waits. So we're going to receive $100 every time we treat a patient, and we incur a penalty cost of $10 per hour that a patient waits. If we figure out their daily revenue here, that's actually pretty simple. We have 45 patients a day coming into the clinic. Each of them gives us $100. We have revenue of $4,500 a day. If we look at the delay cost per patient, a patient waits 0.17 days times 8 hours. That comes out to be 1.36 hours that a patient waits. If the delay cost is $10 an hour, we end up with a delay penalty then of $13.60 per patient. 45 patients a day, we end up with a delay cost per day of $6.13. We can then figure out our margin or our profit of the daily operations. This should remind you basically what we've done with the PCS case. There we sort of tied some numbers to flow through the system, much as we have revenue here. And we could also figure out we also in PCS figure out the delay in different buffers. Here I'm figuring out the delay in the waiting room and putting a dollar value on that. We can now start thinking about possible process improvements. You can go back and check that if we had 3 nurse practitioners instead of 2, we would end up with much, much shorter delays, and the waiting cost delay penalty we're incurring here would drop down to be tens of dollars instead of hundreds of dollars. We may well be able to afford having 3 nurse practitioners, depending on how much they're paid, instead of 2. Let me turn to the other worksheet that we have on the spreadsheet. This has a finite waiting room. So the questions here are about this again, same data with the city clinic, where we have, but now have a limited number of people in the waiting room. If we look at the spreadsheet, the setup is largely the same. We're again entering data where we have yellow boxes. In terms of the basic inputs, the thing that has changed is that we now have to enter the queue capacity. So the first question we're asked is what happens if the queue is 0? So the way this is going to run is that a patient arrives, and if both nurse practitioners are busy, the patient just leaves. If that's the case, then we can figure out the rate at which customers are joining the system, the rate at which people are leaving without being served, and the fraction of customers who balk. That's what I have in the first set of data right after this. We have that sort of the average number joining the queue or joining the system is 28.5. So we're losing 16.5 customers per day. That's 36% of our throughput. We can again figure out the average wait in the queue and the average time in the queue, which is pretty boring when there is no queue. And we can figure out the average utilization of our servers. We're using our servers 57% of the time as opposed to 90% of the time. I should add here, and you can go check this, that because we have a finite waiting room, we could possibly run the system now with just one nurse practitioner, where before that gave us an error message, now that's a feasible number. The second question we're asked is about how large a waiting room do we need to be able to serve 95% of customers. This can only be done by sort of hunting and pecking around with different numbers, and it turns out 9 is the right number here. If we have a waiting room space for 9 patients, we're going to be able to serve 95.3% of arrivals. So we end up serving 42.8 customers per day and only losing 2.1 customers per day. The average number of people in the queue is 2.8, and the average time in the waiting room is 0.0672. You'll note that that's a lot shorter than the wait we had when sort of an unlimited size of queue. The probability that we have more than 0 customers waiting is 66.89, so majority of time there is a queue. Our average utilization of servers is now back up to 85.77, so we get a lot better utilization out of our servers here than we had no queue. The average number of people in the system is 4.5, and again, that is going to be adding up the 1.7 in service with the average. The average number in the system is going to be adding up the 1.7 in service with the 2.8 that are in the queue. And the average time in service is again going to be the average waiting time of 0.067 plus 1 over 25, which is the average service time measured in days. And from that, we can again do a bunch of calculations about whether or not it's worth hiring a third server, what happens if the capacity of the waiting room drops down to 7, etc. I hope you found this useful, and thank you very much.